Welcome dear students, and today's class let us discuss the second question of the very first chapter. First chapter exercise 1. Already we have discussed the first bit about the introduction of Euclid's division algorithm, that is also called as Euclid's division lemma, and some example problems, and also first bit exercise first bit of the three problems we have discussed. And in today's class let us see the second problem. This type of questions are most important question. This type of model question is very important. Compulsory one question from this type of model questions you may get in your examination. Let us see the questions. Question number 2, that is, use division algorithm to show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. We have to show that, we have to prove that. What is that? Any positive integer. You take any positive integer that is in the form of 6q plus 1 or 6q plus 3 or 6q plus 5, where q is an integer. Generally we know that according to Euclid's division algorithm, the standard form is a is equals to bq plus r. What is the standard form? A is equal to bq plus r. Here a and b are any two positive integers. Already we have discussed in the introduction of Euclid's division algorithm lemma. And here q and r, they satisfy this ab values. So that is according to Euclid's division lemma, if we have two positive integers a and b, then there exists unique integers q and r, unique integers q and r, which satisfy the condition, this condition, they satisfy this condition. So already we have checked this condition, and we found we solved some HCF problems also, where 0 less than or equal to or less than b, or the remainder must be equal to 0 or less than b. That is, b is nothing but divisor. Already we have discussed a is dividend, and b is divisor. Now let us enter into this question. Actually here a, for example, a is a positive integer. A is any positive integer. If you divide a by 6, if you divide a by 6, then the quotient 6, then you get remainder r. Yes, here let a be any positive integer, if you divide a, if we divide a by 6, if you divide a is a positive integer, if you divide a by 6 table, by 6, then we get q as quotient. You know that q becomes quotient, q denotes quotient, and r as a remainder. Yes, that only is Euclid's division lemma. Already we have discussed. When you divide a by b here in this standard form, here in this question a is dividing by 6. When you divide by 6, then you get q as quotient and r as remainder. Then we get what would be the standard form. Therefore the standard form will be, what would be the standard form? A is equals to dividing by 6, you get q as quotient and r will be the remainder. But listen to me here. Here what would be the remainders? Remainder always should be lesser than the divisor. Remainder must be less than the remainder. Means what would be the possible values of r? Then tell me, what would be the possible values of r? R would be 0. It may be 1, 2, 3, 4 and 5. Up to 5 possible. Why? Because remainder 6 we cannot get, because we are dividing by 6 table. Then how do you get remainder 6? So not possible. Remainders will be, possible remainders will be 0, 1, 2, 3, 4, 5. So like this, let us discuss the cases one by one. Case 1. Here, when, yes, in the first case, if r is equals to 1, because first odd integer, then when r equals to 1, you get a is equals to 6 cube plus 1. 6 cube plus 1. The result, anything, here it is 6 into something. 6 is an even number. Keep in the mind, my dear student, 6 is an even number. The product of an even number by any number, if you multiply any number by an even number, the result will be even. Then even number plus 1 always gives odd number. Here 6 cube plus 1 is an odd integer. Why? Because just now I have explained, even number, the result will be even number plus 1 is odd number. So here 6 cube plus 1 is an odd integer. And case 2, second case, if r is equals to 3, next odd number 1, 3, and what would be, what do we get? A is equals to 6 cube plus 3. Once again, this result 6 into something gives us even number. This even number plus odd number, even the sum of even and odd, always they give us odd number. Therefore here 6 cube plus 3 is an odd integer. It is an odd integer. And case number 3, let us see third case. If r is equals to 5, next 1, 3, 5, and what would be? A is equals to 6 cube plus 5. Once again, even plus odd. Even plus odd becomes odd. So therefore 6 cube plus 5 is an odd integer. You can write, therefore you can write any number in the form of any number of the form 6 cube plus 1, 6 cube plus 3, and 6 cube plus 5 are an odd integers. Is any integer, any number of the form is an odd integer. So hence it is proved. You can write hence it is proved. It's very clear. It's very clear, my dear students. We have to check according to Euclid's division lemma. So once again, go through the solution and practice this type of questions you may get in your examination. So let's continue one more question. Let us see the second question, third question, that is, use division algorithm to show that the square of any positive integer, is of the form 3p or 3p plus 1. Here we are dividing by 3. 3 will be the divisor. Keep in the mind. In the previous question 6 was the divisor and now it is 3. Once again, use division algorithm to show that the square of any positive integer is of the form 3p or 3p plus 1, but not 3p plus 2, 3p plus 3. So let us see, first of all, what is given. Let us see in the solution what is given. Given any positive integer, square of any positive integer, the square of any positive integer is in the form of 3p or 3p plus 1. So this is given. Let us prove. To prove this, first of all, here let us take, what is the condition? A is equals to b cube plus r. But here 3 is the quotient. According to this, 3 is the divisor. if 3 is the divisor, now here A is equal to BQ plus R, any integer can be represented as 3q plus 1 and 3q plus 2, because observe, according to this Euclid's division algorithm, what is the remainder here? 3q means no remainder, 0 remainder we can get. And secondly, remainder may be 1, it is okay, possible. Remainder 1 is possible when 3 is the divisor. Remainder 2 is possible when 3 is the remainder. Remainder 3 cannot be possible, it cannot be possible. 3 remainder cannot be possible when 3 is the divisor. That's why only the possible cases are 3q plus 1 and 3q plus 2. Now let us find the squares of these numbers. What would be the squares of these numbers? Yes, first of all, 3q. What is the square of 3q? Let us see. Square of 3q is 3q whole square. What is 3q whole square? That is 9q square. But 9q square, according to the question, the square of a number is in the form of 3 into p, 3 into something. Do we get? Let us see. Now 9q square can be written as, yes, 3 into 3q square. I can write 9 is a product of 3 and 3. 3 3s are 9. 9 can be written as 3 into 3q square. Now exactly it is in the form of 3p. So the square of this positive integer is in the form of 3p. Possible. And second case, what is the second case? Case number 2, that is 3q plus 1 whole square. Second one, what is this? It is in the form of a plus b whole square. As you know, a plus b whole square is, write the formula first. A plus b whole square is a square plus b square plus 2ab, or a square plus 2ab plus b square. You can write like that. Now here, just apply the formula. You get 3q square plus 1 square plus 2 into a into b. Now what would be the result? 9q square, and it is 1 square is 1 plus 2 3 is a 6q. Now let me write this 9q square plus 6q plus 1. Why plus 1? I am shifting to last at last, because we are going to prove this would be in the form of 3p plus 1. 1 should be separated. Now let us take 3 as common factor. Exactly 3 is the common factor for 9 and 6. 3, if you take out 3, we get 3 3s and 3 2s plus 1. Once everybody observe this form, this is 3 into something plus 1. So therefore 3 into p plus 1. So 3p plus 1, that is also in the form of 3p plus 1. So second one also in the form of 3p plus 1. And third one, 3q plus 2. Let us check the third case here. Just check the third case, that is 3q plus 2 whole square. Once again, a plus b whole square formula. A square is 9q square plus 2 a, what is a? 3q into b 2 plus b square 2 square. Just follow that concept, follow that steps. Now it is 9q square plus 2 3 is a 6, 6 2 is a 12, 2 3 is a 6, 6 2 is a 12q plus 2 square is 4. Yes. Now let me write 9q square plus 12q plus 4 is written as 3 plus 1. Why plus 1? To get 3p plus 1 form. To get form, to prove that form, we are taking 4 as a sum of 3 and 1. Now observe the first 3 numbers. They are all the factors of, they are all the multiples of 3. They are all the multiples of 3. So therefore 3 is a common factor. You can take 3 into 3q square, 3 4s are 12, 3 1s are 3 and plus 1. Observe this last one, it is in the form of 3p plus 1, hence it is proved. Hence it is proved. What is proved? Any number, any positive integer in the form of any positive integer, the square of any positive integer, the square of any positive integer in the form of 3p or 3p plus 1. Compulsory that would be in the form of 3p or 3p plus 1. So this is the solution. So you can go through this model. Questions are important, already I have told you. We have just 3 to 4 questions are there. Once you go through the example problems also, you better to practice twice and thrice, then you will get perfection. Let's go to the next question. Yes, and the next question number 4 is use division algorithm to show that the cube of any positive integer is in the form of 9m, 9m plus 1, 9m plus 8. Square we have discussed in the previous question. Now at present, show that the cube of any positive integer is in the form of 9m, 9m plus 1, 9m plus 8. Yes, let us see the solution. First of all, as you know, A and B are any two positive integers. Suppose A and B are any two positive integers where B is equal to 3. Where B is equal to 3, we are going to take 3 because 9 is 3 multiples. So therefore you should take B as 3. Now the divisor is 3. B is equal to 3. According to Euclid's division lemma, we know that according to division lemma, yes, that is A is equals to B cube plus R. But now A is equals to, what is here, you know that what is R value? R is always less than or equal to 0. 0 is less than or equal to R and less than B, you know that. And here A is equals to B. What would be B here? That is 3q plus R. Then once observe this condition, then what would be the R value? Therefore R value should be, remainder may be 0, possible when 3 is divisor. Remainder 1 is also possible when 3 is a divisor. Remainder 2 is also possible when 3 is the divisor. Remainder 3 cannot be possible when 3 is the remainder. You know that. Is equal to 3q plus R and R values will be 0, 1, 2. First case when R is equals to 0, when remainder is 0, we get, what do you get? A is equals to 3q because remainder is 0. Now according to the question, cube of, now let us take cube. What would be the cube? Cube of 3q is 3q whole cube. What is 3q whole cube? 3 cube, q cube. 3 cube, 3 3s are 9, 9 3s are 27 q cube. Now 27 q cube is the cube of this number, and this form you should convert into in 9m form. You should convert into 9m form. Means this result would be the multiple of 9. Let us see. Now 27 can be written as 9 into 9 3s are 27, 9 3 q cube, 9 3s are 27 q cube. Means it is in the form of 9m. Exactly, it is in the form of 9m. Let us see the second case, case number 2. And what is that? If R is equals to 1, R is 0, is finished. Let us take R is equal to 1. Now just put R is equal to 1 in this division lemma. We get A is equals to 3 cube plus 1. Now again cubing on both sides, you get cube of this number 3 cube plus 1 whole cube. It is in the form of A plus B whole cube. Be alert. Write the formula first. A cube plus 3a square b plus 3ab square plus b cube. This is the formula of a plus b whole cube. Now put the values of a. The first one is a and second value is b. Just put the values in this formula. We get 3q whole cube plus 3 into a square, that is 3q square into b is 1, and next 3 into a. What is a? The first value is a into b square, that is 1 square, plus b cube, that is 1 cube. Let us simplify this. 3q whole cube is 27 cube. Already we have done in the previous step. Next, 3q whole square. Simplify the bracket first. Don't get confused. Don't multiply this 3 into this 3. First, what is 3q square? 3 3 is a 9q square. That 9q square into 3. 9 3 is a 27q square. And again here 3 3 is a 9. Q into 1 square is q plus 1 cube is 1. Now once observe all the values, all the first 3 values. In this we have got 4 results, and observe the first 3 terms, all they are the multiples of 9. Just you take out 9. Take 9 as common factor. We get 9 table. 9 3 is a 27 q cube. 9 3 is a 27 exactly. 3q square. And 9 1s are 9, you get only q, that's all, plus 1. Now once observe this is 9 into this whole bracketed, you can take as m, plus 1, hence it is in the form of 9m plus 1 exactly. So second case also is finished. Let us go to third case. Observe here properly third case. Once you copy all this, then immediately I go for third step, that is third case. Third case, that is a is equals to bq plus r, that is 3q plus r. But what is r? If r is equals to last value 2, that is 2. Once again cubing on both sides, we get 3q plus 2 whole cube. Just find the cube of this binomial. Just like this, write the formula and put the values. We get a cube, first value cube, b 3a square b, 3 into a square into b, plus the formula is 3a into b square, 2 square, plus 3a square b, 3ab square, and last b cube, that is 2 cube. Let us simplify this. 3q whole cube is 27q cube plus 3 square is 9. 9 3 is 27, 2 is 54q square. Just simplify properly. And 2 square is 4. 4 3 is 12, 12 3 is 36q. And finally 2 cube is 8. Observe all the first 3 except the last number 8. And what do you get? What do you have here? Except the last fourth term, remaining terms, check. They are all multiples of 9. You take 9 as common factor. 9 3s are, 9 6 are 54, 9 4s are 36, that's it, plus 8. Now once you can take this whole bracketed value as m plus 8, hence 9m plus 8. So therefore the problem we have proved that the cube of any positive integer is of the form 9m, the previous concept, 9m plus 1, and the third case 9m plus 8. So like this 3 cases we have proved. You can write hence it is proved. Hence it is proved. This is one of the important essay type model question. So my dear students, this when you listen this you can understand, but when you put on the paper you cannot. So try to practice twice, thrice and 4 times and 5 times till you get. That's it.